through our top-level system design. So it all begins at our USB camera made by Gigaware, and that outputs a 160 by 120 RGB image over USB to our Windows PC, where we use MATLAB to process this. And so we have two MATLAB scripts, the first of which is the initialcam, I guess, that initializes the port, the serial port, and the camera. And the second script takes the 256 RGB video, gets the current snapshot of it, and downsizes the video into 8-bit color using these simple bit shift operations. From there, we serialize the data and send it over UART to the FPGA board. So once the signal is received by the FPGA over the UART, it is loaded into the block RAM, where it is stored up until the image is fully transferred to it. After that, it is sent over the VGA to our monitor, where you can view the live streaming video.
One of the things we wanted to implement is make sure that once we write an image to the VGA monitor, that image stays on the monitor until the next image is written to the VRAM. So how we actually accomplished this was by writing a small finite state machine that switches between two states. In the first state, the first VRAM is being written to while the second VRAM is being read from. And then in the second state, the order of these VRAMs switch. So any time that we're displaying an image on the screen, that image is being read from, and simultaneously we're acquiring a new image from the other VRAM, which is being written to. So I'm going to tell you about how we're actually writing to our VRAM module. So in this piece of code here, in this always block, every time we receive a new byte, it gets written to the VRAM, and then the address is incremented. Once we reach the edge of our VRAM module, the address is reset to 0, and we have a flag that goes high that tells us our VRAM is full. Once the flag is high, then we write the VRAM is written to, and we display this on the VGA.
I'll now walk you through the image processing functionalities we implemented on our FPGA. So the first function we implemented was the grayscale. As you can see from our code, we used a simple lookup table to implement the grayscale. If we go to the lookup table, you can see that each input RGB maps to a output RGB using a specific transformation matrix calculated in MATLAB. The second filter we implemented was the sepia filter. Basically, it adjusts all the RGB values to display a yellow hue over the picture. Similar to the grayscale module, we used a lookup table to implement this, mapping the inputs and the outputs using a transformation matrix. Next, we implemented the inverse filter. This filter simply takes the RGB value and subtracts it from the max RGB values, giving you the inverse color for each pixel in the image.
Yeah, challenges, I think, is in general.
One of the more complicated image processing filters that we implemented was the Obama filter. As you can see here, the Obama filter separates the image into 5 discrete color values: white, gray, blue, light blue, and red. Depending on the input RGB values, it will set 5 discrete thresholds and change the color to be within whichever threshold it's in. This was implemented simply by many if statements in code.
So here we have our mirror filter. Basically what this does is, as the VRAM is being read from, it increments through the address. Once the H counter reaches to the halfway point, it decrements that same address, and once it reaches the edge of the image, it adds the row length to the address to reach the next row of the VRAM to read from. What this ends up doing is it creates a mirrored effect on the image.
As you may have noticed before, all the image processing done was done on live video. We also implemented a capture button which allows the user to flip a capture switch which will continuously show the same image on the screen, allowing for the user to process just that image. Once you flip the switch back, normal video resumes.
So one of the trade-offs that we were playing with was how do we keep the image from taking too long while still maintaining a decent size to be displayed on the VGA. So what we did was we stuck with a smaller resolution image and we double that on the VGA screen. So we've written an always block that essentially displays a pixel from the BRAM twice before it increments the counter, the address counter to display to the VGA monitor. So what we do is we display each pixel twice by row and then each row twice.
Due to the fact that we cannot directly interface our camera with the board, we have a large latency. I will now show you how we measure this latency.
Actually, it's better.
As you can see here, we'll start the timer at 0, and we'll see on the screen at what time this appears.
That's fine.
So I'll start the timer right now. The first value appears at 4.3 seconds. The next value appears at 9.8 seconds, showing that our average latency is 6 seconds.